To understand the scale of a modern electrical grid, you have to look past the wires and into the generator rooms. Unlike a simple battery that pushes current in a single, steady direction, these industrial systems operate on a massive, shifting exchange of energy. This entire infrastructure is built on an idea from Nikola Tesla, the rotating magnetic field. By spinning a magnetic field at a constant rate, Tesla created a way to generate power that moves in repeating cycles. This led to the first practical induction motors and the standard use of alternating current, or AC. In an AC circuit, the voltage doesn't stay flat. It rises to a peak, drops to zero, and reverses direction, creating a repeating sine function over time. As long as you only have one component, that wave is manageable. But a real-world circuit involves thousands of components, each interacting with these rapid, periodic reversals at different moments. Analyzing these overlapping sine curves using standard algebra is incredibly difficult. Because each wave is shifting and reversing at its own pace, the math becomes a chaotic tangle of horizontal offsets and intersecting lines. To make sense of this, we need a way to stop the clock, a method of turning these moving, time-based waves into static geometric shapes that we can actually measure. We start with the baseline, a source of AC voltage connected to a single pure resistor. According to Ohm's law, the current in this specific circuit is a direct reflection of the voltage driving it. Because they are perfectly synchronized, we say they are in phase. Both the voltage and current reach their 0 points, their maximums and their minimums at the exact same time. This graph shows those two distinct waves. Even though they have different heights or amplitudes, their peaks and valleys are aligned on the timeline. This alignment is simple for a resistor, but complex components like inductors will push and pull these waves out of sync. To track that shift, we use a geometric construct called a phasor. A phasor is a rotating vector, an arrow that spins around a center point at a constant angular speed, symbolized by the Greek letter omega. The total length of this arrow represents the peak amplitude, or the maximum value that the voltage or current reaches during its cycle. The rotation speed of the arrow is directly tied to the frequency of the AC signal. One full cycle around the circle represents one full cycle of the wave. The most important part is the vertical projection, the shadow the arrow casts on the y-axis. As the arrow rotates, the height of that shadow gives us the instantaneous value of the current at any given millisecond. By representing a wave as a rotating arrow, we've translated a complex, changing flow of time into a simple relationship between length and angle. This side-by-side view shows how those rotating arrows actually generate the breathing sine waves we see on an oscilloscope. As the arrows spin on the left, their vertical heights are traced onto the moving timeline on the right. In our pure resistor, the voltage and current phasors point in the same direction. They are locked together, rotating in perfect alignment. Because they point the same way, their vertical shadows rise and fall at the exact same rate, ensuring the resulting sine waves peak at the same moment. In this case, the separation between the two arrows is 0, which we call a phase angle of 0. This diagram acts as a frozen snapshot. It tells us the relative timing of every wave in the circuit, without us having to plot out the entire timeline. This snapshot is vital when we introduce components like capacitors, which act as a sort of electrical buffer, causing the current to reach its maximum slightly before the voltage does. On a standard graph, this looks like two waves shifted horizontally, making it difficult to calculate how they will interact at any single point. But on a phasor diagram, we just measure the angle between the two arrows. In a pure capacitor, we can clearly see the current phasor sitting exactly 90 degrees ahead of the voltage. By focusing on that single angle, we can predict how these components will behave using simple geometric observations rather than tedious trigonometry. It is important to remember that voltage and current are scalars, not vectors. They don't have a physical direction in space like wind or force. We use these arrows because their mathematical projections happen to model simple harmonic motion with efficiency. It's a way to align the abstract math of electricity with how we perceive geometry. This concept is what allows you to tune a radio. By adjusting the internal components to change these phase relationships, you can filter out millions of competing signals, isolating the one frequency you want to hear. From the spinning magnets in a power plant to the tiny filters in a smartphone, phasors are the tools that allow us to map the invisible, changing flow of alternating current into a language of predictable geometry.